All right, the next thing we're going to talk about is uh, have you refer to a graph on page 461 of your text on part 3. Uh, that the way that the graph is arranged, it's kind of strange because in terms of energy, you would think if you're wanting to talk about something more stable, that would be at the bottom of the hill. So, and that's normally the way that we end up drawing things. But for whatever reason, and it is totally universal, every chart you see is drawn this way. It's upside down. So in this situation, the most stable nuclide per nucleon is at the topmost point instead of the bottom. So if you're looking at that graph, then you end up seeing up in the iron, nickel, zinc region is where you get the peak there, and you end up having it fall off on both ends. So we'll first talk about the left side. As you increase, so as you, Jesus, okay. As the number is going up on that table, sorry, the backwards thing with this camera I cannot get used to. As the on the left side of the table, you'll end up seeing the numbers increase, so it becomes more stable the higher the charge on the nucleus, up until you get to a charge of between 26 and 30, which is your between iron and zinc. So as if you have enough energy to be able to overcome the Coulomb barrier between the two, that it's energetically favorable to end up starting have these grow to higher and higher charge until you get to iron. And we'll end up talking that process of increasing the charge by building up a nucleus. Being energetically favorable, it's called nuclear fusion. We will address nuclear fusion a little bit more whenever we talk about what happens inside of stars. That it turns out that nuclear fusion, again, because that the nuclei, remember, they're really, really small, so, and that they have to get really close to end up feeling the strong nuclear force to be able to bind together. So they have to have a tremendous amount of kinetic energy to be able to bring them together to be able to start to bond together. So it's that it's not very easy to do at all. That's why it's taken decades to be able to build something, and the hope is that they're going to end up having a functional experimental fusion reactor somewhere in the 2020s that's called the ITER reactor. So, but it's in order to be able to do the very coolest one that is practically doable on Earth, it would need to be a deuterium, either deuterium-deuterium or deuterium-tritium reaction, and those operate at temperatures from about 50 million Kelvin for deuterium-tritium up to about 400 million Kelvin for deuterium-deuterium. So it has to be incredibly hot to be able to do that. You also then have to be able to hold it in place so it doesn't fly away. You have to keep them together to be able to react. So it's a significant technical challenge to be able to do. The advantage to that is that there's a whole lot of deuterium because that's just an isotope of hydrogen. So there's more deuterium than we could ever use on planet Earth. Helium-3 is a better one than deuterium is. The problem is helium-3 is very, very hard to come by on Earth. The reason for that is that we have on Earth thorium, uranium-235, uranium-238 are naturally occurring. They're alpha emitters, and so the alpha emitters will end up then spitting off helium-4. So where you get things that trap gas come up from the interior of the Earth, you get this constant flow of helium-4, and there's nothing producing helium-3. So the helium-4 overwhelms the helium-3 available on Earth. That's about the only thing that is conceivable where mining the moon actually ends up becoming useful, because the moon doesn't have all those heavy elements in its interior. So the helium percentage is still more helium-4 than helium-3, but the helium-3 percentage is drastically higher on the moon in terms of the helium available than there is on the Earth. So anyway, then for the other direction, so on the other side of the chart, you end up seeing on the far end you've got uranium coming back up toward iron. On that end of the chart, that the heavier your charge, the less stable it is. So that means that energetically it's favorable for things that are very heavy, very high charge to be able to split apart. Now it takes a lot of reorganization for that to happen, though. So it's not going to be the ones that are pretty close. It's going to be the ones that are the really far end that have a chance to be able to do that. We've already talked about spontaneous fission before. For extremely high charge, that if it's high enough, there's always a shot that's going to just blow itself apart directly. What we're going to talk about next, though, is a little bit different. It's called induced fusion. And when we have that, we end up having a nucleus, and where a neutron comes in and interacts with a nucleus. That it's pretty much always going to be the case. If a neutron comes into a nucleus, it's going that the free neutron has really, really high energy. So whenever it binds, it's going to drop in energy. So the nucleus will be energetic, basically no matter what it is. What's different about certain things, though, is that for a few nuclides, that can end up causing the nucleus to become so extremely energetic that it becomes really likely, whenever it wiggles apart, for it to be able to get into the kind of mode where it pinches off, so that then the electrostatic repulsion splits apart to two little bits. And for that to happen, in general, the nucleus needs to have an even charge, because we mentioned that that protons like to pair up. So there it would end up needing that in order for your original thing to be stable enough that it doesn't just blow itself apart already. But it also needs to have an odd number of neutrons, because the pairing energy there ends up increasing the amount of binding that you get from it. So it ends up becoming more energetic when that happens. And the nuclides that do this really effectively are uranium-235, which is naturally occurring, your plutonium-239, which ends up being your text ends up showing you how a breeder reactor works. And also uranium-233, which would be produced by a breeder reactor from thorium-232. So these are odd numbers of neutrons. So if a neutron comes in, it becomes an even number. It's happier being even. So that means there's more total energy. It causes the thing to have a high probability of splitting apart. And whenever it splits apart, as we talked about in spontaneous fission, that it ends up being connected by a little chain of neutrons in between. So because of that, you're going to end up having free neutrons that fly out when that happens. So you put a neutron in, and you get neutrons plural out. So if you have a scenario where you have a high enough concentration of these uranium-235 nuclei, or one of these that are fissionable, that one of these neutrons then gets absorbed by the next one. It becomes energetic, blows apart. The next one becomes energetic, blows apart. So you end up getting a chain reaction. And the chain reaction can end up being one where you end up getting just a few, uh, uh, or you get a few uh, uh, neutrons produced, so it's pretty much even whenever you have one particular kind of geometry, or if the density isn't as high, so you get a chance for them to escape, or they get absorbed by other stuff. Uh, in that situation where it continues, there's enough to be able to for it not to peter out. We end up saying that would be a critical point of the reaction, so it's just able to keep going, which is what you do in a nuclear power plant. If you have higher amounts still, then you end up getting chain reactions that are uncontrolled. So, depending on how much excess you have, so a if it's 10% excess or whatever like that, 10% more produced than is absorbed, then you end up getting situations roughly like what happened at Fukushima Daiichi, where you end up having reactor meltdown. If it's much higher than that, then you end up getting either a neutron bomb or you get an atomic bomb. Whenever it's at 90% helium, 90% uranium 235 or plutonium 239. All right.